In this video, we will evaluate some points on a logarithmic function and use that to create the graph, and we'll figure out the domain and range and talk about that one last time. So let's let our function be log base 2 of x, picking a fairly simple base just to help see the nature of the graph of such functions. So let's say we wanted to plug in certain numbers, and in this you'll see I've picked very specific numbers to plug in, because if I just start plugging in random numbers willy-nilly, chances are they're not going to create anything easy to figure out. And much like an exponential function, there's certain numbers that, it's kind of like with squares and square roots. Only certain numbers work nicely, and that's why I've selected, the numbers that I've selected here. So first off, let's try, if x is 1, that would mean I would be trying to find what's log base 2 of 1. And remember that log of 1 is always 0, because 2 to the 0 power makes 1. And that's always how you do a logarithm. You want to think 2 to what power makes this? And anything to the 0 always makes 1. And then and actually this gives us our x-intercept on the graph, because if I start at 1, I would get 0. And that's something to remember about logs, is that their x-intercept is, again, unless they've been translated, moved around, or something like that, is typically going to be at 1, just like how the y-intercept for an exponential was at 1, when we were working on these before. And so, as I said here, the y-intercept is 1. Well, in a logarithm, since the logarithm is an inverse, it's got the reverse relationship, it's going to flop the intercepts. Now, if we were going to do log base 2 of 2 next, now when we have matching, that's always 1, right? Because 2 to the first power makes 2. So this would give me the point 2, 1, which would be right about there. Log base 2 of 4. Again, we think, what exponent do I need? Well, 2 squared is 4, so answer is going to be 2. So that would give me the point 4, 2. Log base 2 of 8 would be 3, right? Because 2 cubed is 8. And for 16, log base 2. So notice the numbers I've chosen are all powers of 2. Because sequentially, right, all those numbers are going to give me the respective integers. Because 16 is 4 2's. And the next one would be 32, right? Log base 2 of 32 would be 5. And so on and so forth. But basically, these are giving me some easier points to graph on my curve. And then if I was to do 1/2, log base 2 of 1/2, since 1/2 is the reciprocal of 2, that would be -1, right? Because 2 to the -1 makes 1/2. And so that would be another point. This one's a little harder to graph, but if I go in between 0 and 1, I would go down to 1/2, or -1, which would be right there, so right about there. I would have that point. And basically what will happen is, again, this is another property of inverses that we discussed back in 2.7. But remember that the graph of an inverse is always is the same graph, but it's reflected about the line y is equal to x. And the shape of a logarithm is the same shape as that of an exponential. It has the exact same graph. It's just sort of sideways and flipped over. And also, since, if we're talking about stuff like domain and range, recall that an exponential function had a domain of all real numbers. Everything worked in there, but the range was only 0 to infinity, because it only worked in those intervals. Sorry, let me try to write this a little bit more carefully. And as I said earlier, this was quite a bit earlier when we were talking about the properties of inverse functions. But remember that the domain and the range for an inverse functions must always be exactly opposite. So if we were talking about what is the domain and the range of a logarithmic function, it would be exactly the opposite. The domain is 0 to infinity. Kind of like how I said a minute ago, negatives do not work in logs. 0 does not work in logs. Meaning its domain only works for positive numbers. And the range is actually all real numbers. Because notice, like, for the inputs, I only used positives. Well, And I get, again, I didn't try 0, but log base 2 of 0 for the same reason is undefined. And log base 2 of -1 is not real. So those were sort of trick questions, but basically these ones are not part of my graph. So all that's being said is that those are not part of the domain. And or again, just in general, you could just memorize the basic domain. And I think what's an easy way to remember this is sort of it's sort of like a square root function. A square root function only works for positives, though the only difference is a log. It only works for positives, but it does not work for 0. The square root does work for zeros, but the log does not. But otherwise, it's very, very similar. And the range is always all real numbers. And again, you could graph these with your calculator. So say I wanted to graph log base 2 in my calculator. I could always just go in here, type in log base 2 of x, and just look at it right like that. But again, I would get a very similar shape, but it's an exponential curve, just backwards. And that property of symmetry was that if we reflected about the line y is equal to x, we'll get the same exact graph. And that's what I wanted to do with this last little part over here, which says to use a calculator to compare the graphs of e to the x and ln of x. So if we wanted to do that, we could graph e to the x by typing in first. And we graphed this one by hand a few videos ago, but it will have the basic shape of an exponential curve, flattening off to the left, exploding up to the right. And if I wanted to graph ln on the same axis, I could do that on y2. And that would give me the graph of our natural log, which again has pretty much the same shape, right? Because the only difference between this and ln is base e 2.7, whereas this is base 2. So they're very, very close. And also, if I graph alongside of this the line y is equal to x, remember that was the line of symmetry between a function and its inverse. And we can see that those graphs are the same on either side. And especially if we zoom square, it will fix the skewing of the graph. And we can really view the symmetry. But it's all because of remember this property was because input and output, right? For an for an exponential function, when you plug in 0, you get 1. For a log, when you plug in 1, you get 0. It's the reverse point. X and y are interchanged. And every other point has x and y interchanged. When you interchange x and y, this is what always happens. So that, like in the next video, that will wrap up lecture for this week, because this has been more than enough for a couple videos. And in class this week, we will talk about solving exponential equations, and actually applying this to some real problems. And then in next week's lecture, we're going to talk about log laws. We're gonna skip around just a little bit in the next couple days, but for now, that's good. Focus on exponentials, logarithms, how they work, how to evaluate them, and just really focus on understanding graphs and the properties of these functions.